Welcome back to Machine Translation. Today we're going to look at corpus acquisition from the internet. So for many language pairs, lots of text is available. So here's to give you some idea about the dimensions of text that machine translation systems can be trained on. So if you just do a kind of back of the envelope calculation, assuming you read about 10,000 words a day, you will read in your lifetime 30 million words. The amount of translated text available for some language pairs goes into the billions of words, and the amount of English text, just monolingual text available, is in the trillions of words. So where do we get this text from? Well, we get it from mining the web. So the largest source for text you can have ready access to is the World Wide Web. And there's actually a commonly available crawl of web content uh, that is called CommonCrawl. It's publicly available. It's a crawl of websites. It's hosted by Amazon Web Services, but you can also download it from there. It is regularly updated. It says here semi-annual. It fluctuates a little bit how often it's updated. More recently, it's updated more frequently. And in each of these crawls that are being released, about 2 to 4 billion web pages are being released. So this is one of the corpus that are currently filling up hard drives in our lab. So this is what this corpus is. The starting point is in the order of 35 terabytes of text. So then you can pass this through a processing pipeline, which consists of first running language detection, then deduplication, then normalizing of Unicode characters. There's a lot of messy things with encodings happening. Unicode has been the standard now for quite a while, but there's still ancient web content that is in various strange ASCII formats. And even in Unicode, there are several ways how you can actually encode the same kind of characters, especially if they're things like accented characters or otherwise combined characters. This is a very messy topic. And then a sentence splitting. So now we just talk about monolingual data. That's the last processing step. We probably want to split things up into sentences, which is also not trivial. So here is the amount of corpora that were obtained in this work that we are citing here. So for English, that is 59 billion lines of text, almost a trillion words. And if you actually look at this in bytes, this is how much data you get. Then there is significantly less text available for other languages, but the other big languages like German, Spanish, French, Russian, Czech, still fairly large amounts of text are available, still in the order of 50 billion tokens. So we're still talking about here 100 times more than you can read. So you will not be able to read all this text, even if you spend the rest of your life doing that. In this paper here, we also compared it to what happens if you add this as a language model to machine translation. So we do this for English-German system, English-French system, English-Russian system, English-Czech system. So just having this additional monolingual text did give significant boost in translation quality. So why don't we just use this resource to also extract parallel text? So here's an early effort where we did this. So it's a fairly basic processing pipeline. So first step is to find parallel web pages. So there's all these web pages, they're all crawled, but which ones are actually translations of each other? The simplest method you can try is to look only at the URL. So just match things by URL and check if there's like something that says lang equals en for English language and then lang equals fr for French. And that's the only difference in the URL. That is often a very good indication that these are the two translated documents. You could also align documents by HTML structure. More on that later. The next step, at this point, you have a pair of documents. So you have one web page here, another web page here with a particular URL. Then you want to split this into sentences and also tokenize it. And the next step then would be sentence alignment, finding out which of the sentences in the document are aligned to which of the sentences in the aligned document. And finally, you also maybe want to remove some boilerplate or otherwise bad sentence pairs. So this is this rather early work where these are fairly basic steps. And this is how much data was collected there. So this is the number of segments or sentence pairs. And it's a significant amount for French, 100 million words, less so for German, Spanish, and so on. And for really low resource languages, we did find some data, but not all that much. So there's definitely much more work needed to pull this off, and this is something we actively work on right now. Maybe I should say at this point also something about data cleaning and subsampling. So not all data is useful. Some may even be harmful. More on that at the very end of this talk. So you could remove data based on domain relevance, alignment quality, redundance. You don't want to have the same sentence pairs over and over again, or just bad language, or machine translated or poorly translated output. So when you remove bad data, you can actually train your models faster, and removing bad data sometimes helps quality. Actually, we have realized in the context of neural machine translation, removing bad data does significantly help quality very often. So just having a clean data approach, so only using high quality data, helps especially in limited domains. Okay, let's walk through all these steps I outlined in a bit more detail, and let's start with corpus crawling. So, first of all, finding monolingual text. So the simple idea, download as many websites as possible, extract text from HTML, guess the language of the text, and then add to the corpus. And voila, profit. So we just want to collect now a lot of text from the internet. This sounds very simple, but it turns out that these steps are actually quite involved. So, we start here a little bit guided by what's available on CommonCrawl. So this is, as we already said, a non-profit organization and has data publicly available on Amazon Web Services. So it has released data in several crawls. For instance, the January 2015 crawl has 140 terabytes or 1.8 billion web pages. So the way they collected this, they used a crawler called Apache Nudge and had a list of predefined URLs that they just visited. So next step is extracting text. So here's a web page of some random website that might look familiar to you, at least as a style of a web page. So it's not just text on it. There's all kinds of visual elements, and text is organized in like headlines and subtitles and then actually blocks of text here, but also a lot of these navigational elements. So this is how it really looks like. This is the HTML source, so which has all kinds of additional markup information that says something about how the text should be displayed. So for instance, there's a date here that is being displayed as text, but then also has some additional kind of meta information here. Of course, there's meta information about links and so on and so on. So why don't we just remove all these tags? So we remove all the tags and replace them with spaces. And if you had multiple spaces in a row, we condense them into one space. This is what you end up with. So there's some tricky cases here. For instance, the word yes. So why did that happen? Well, this is how it was written in HTML. This is how it looked up on the screen. So this is definitely a case where we need to merge that. But in other cases, like here, we don't want to merge the spaces. So that's a bit of a tricky problem. Then there's also this here, which the stuff here at the end, which doesn't really look like a proper sentence. And it might be hard to extract that out. So one way to deal with that is using an HTML parser that is aware of what different tags are and what they mean, and then based on these HTML elements, you could break things up. So there are clearly things like paragraph breaks that separate paragraphs, so these should definitely be sentence splits. And there might be things like bold tags or italic tags. They definitely shouldn't indicate sentence breaks or character breaks, and they should just completely be removed without any trace. Okay, next step is language detection. So what language is this text in? So you may not know this language, but you do discover things like this here that are definitely somewhat peculiar. Looks a little bit like Spanish, but actually is Portuguese. And the real indication is that these letter n-grams really give this away. Maybe there are also particular uh, typed extended characters that only exist in particular languages. So it looks a lot like Spanish, but Spanish doesn't have these kind of character sequences. So the basic, most common way to build a language ID is just go by character model, a character-based model that just looks at letter n-grams. So there's actually a Python library that you can readily use to do this. And so you can actually feed it multiple things and see what it predicts. So if you say here, muitas intervenções aleatórias, then it predicts Portuguese with pretty high confidence. If you only give it 2 words, it still predicts Portuguese with fairly high confidence. If you just give it muitas, it actually predicts English. So language ID works as long as the input to language ID is long enough. And that's somewhat intuitive, because if you just have a single word, it might actually be a valid word in many, many languages. So here are some examples for language ID. So there's langid.py, so that's like a Python tool that uses 1 to 4 grams over characters, naive Bayes, and has also some feature selection. Another one is called TextCat, which is similar to langid.py, but it doesn't have feature selection. And another very common tool is CLD2, or there's now a CLD3 out even. That's the Chromium language detection by Google. That also looks at hints from top-level domain and metadata in HTML. It's super fast and also breaks things down. If you feed it a document, it can actually say for specific spans of text, this span is English, the next span is Portuguese. So if you run this over CommonCrawl, this is what you get. We excluded here English because that would have not fit on this slide. And this is using Google's CLD2. So it has a lot of German, Spanish, French, and then it kind of still has mostly European languages, but also Japanese, Chinese, and then Arabic, and further down other languages. Basically, if maybe also interesting, if you look at the text you get out of this, well, you get a lot of stuff that is just repeated over and over again. So if you just look at things like add to or share or unblock user, these things occur excessively frequently. Add to occurs as a line over 1 billion times in the corpus. And apparently WordPress is probably a tool because that line occurs on 60 million times. So here is some example of if you added a really large English language model to a statistical machine translation system, what gains you get. So basically, the more data, the better. This is something that has been shown here for neural MT. So for statistical MT, you see that the amounts of data double each time, and the gains are always somewhere between 0.2, 0.3 blue points. And that's also something we observe with neural machine translation. More data always helps. Okay, so we handled monolingual corpus crawling. Let's move on to bilingual corpus crawling. So we want to mine bilingual text. So bilingual text is the same text in different languages, so the meaning expressed in different languages. Usually what happens is that one side is a translation of the others. So one side was created first, and the other side was created by translating the other one. It might be the full page that is being translated, or just the interface, or just the content. Sometimes it's possible to have actually the translations on the same page. So people might make Twitter or Facebook posts where they say the same thing in two languages. You can see this, for instance, by celebrities whose native language is not English. They often post things in their native language and then also in English to make it more broadly accessible. So here's the basic pipeline for that. So first of all, identify websites worth crawling or worth processing. Then crawling that website, language detection as before, extract text from HTML as before, but now the additional steps is to align documents, align sentences, and then clean the corpus. So let's start with the first step, identify websites. If you're a bit familiar with what's out there, you realize that there are few websites that have massive amounts of really good, useful parallel text. And there have been already pretty dedicated efforts to get this. So the European Union is a famous source for parallel text because they have over 20 official languages. For instance, the European Parliament has been a source for parallel data to boost machine translation research for almost 20 years. There is in Canada the Parliament proceedings called Hansards that are published in English and French. The United Nations has 5 official languages, and there are other kind of multilingual news sites like Project Syndicate. There are TED Talks where volunteers translate stuff. Another big source is volunteers translating movie and TV show subtitles. Global Voices is another kind of news site where volunteers create translations. So since these are kind of high quality, large kind of resources of good text, people actually went into and wrote by hand dedicated tools to crawl, text extraction, document alignment. Once you look at a particular website, you can then just look at URLs or link structure to kind of align documents just by kind of analyzing how this website is organized. It does take a few days of effort per site to set this up properly. So what if you don't want to limit yourself to this handful or maybe dozens of really very useful websites with good quality content, but to go out to the web? So you want to identify many websites that are worth crawling. You only going to realize if they actually have parallel text once you crawl them. So here's some tricks. If a website has the line "this page in English" or "this page in German" or "this page in French" on it, probably it has multilingual content. So you can just put this query into Google and it'll return a bunch of documents, and then you can go out and crawl the corresponding website. Another one similar thing is if it has a link to a language flag, maybe that's also an indicator for here's the French version, here's the Spanish version, and so on. Another strategy is to just look at what we have already available in CommonCrawl. And if there's a website that has content in multiple languages, maybe that content is translated content. So we should either take all this stuff from CommonCrawl or recrawl the website. Once you start crawling a website, you basically do this by starting at the start page and then follow links. So you could do this by kind of figuring out how deep you should crawl it, because you don't want to be trapped in loops and getting the same pages over and over again. So you can limit it by saying up to n links deep into the site, or maybe you just follow up to n links in total. Also, maybe make sure that you only follow links to web pages, not images. That would cause you to download a lot of content that you then can't really process and have to throw away. And you also might want to avoid crawling websites too deeply that do not have any parallel text. So that would require some quick feedback from downstream processing. So once you already collected maybe 1,000 URLs, followed 1,000 URLs on a website and got all the documents and all of them are in English, then maybe you should stop doing it, because there's probably no foreign content on that website at all. Okay, let's move to the next step, document alignment. So this work goes back to over 20 years ago. So there was a tool called Strand, which means structural translation recognition, acquiring natural data, by actually researchers down the street at the University of Maryland. So their pipeline was candidate generation, candidate ranking, filtering, and then optional also sentence alignment and evaluation. So one thing one feature that took into account was link structure. So what if there's a page that links to different language versions? So it has a link for English, French, and Spanish that links to the different versions of languages. And then these are, if they're basically from one page, links to content in different languages, then maybe that linked content are translations of each other. Here's an example for that. So you can go to the support for Apple page, and it has all these different links to countries now, and mostly different countries have different languages. Then there's also this idea of sibling pages. So you have here one website that on the top has also language links, and then when you click on this, you get directly the corresponding page in the other language. Another thing is to look at the URLs. So I already mentioned that. That's a cheap feature. You can just look at this URL here, if there's a /en, and then there's also a /fr, or there's like lang equals fr, then you can map that up. Another one is there's a website with .com, and then the same website or domain name with .fr. Here, obviously, the cat and le chat is much harder to link up. But you can write a few rules to kind of identify these things, and then that's going to help you to actually gather quite large amounts of parallel web documents. Here are a bunch of patterns that could be used. Lang equals en and various variants of that. HL is apparently used, locale, and so on and so on. So here are all kinds of patterns from URLs that have lang and maybe something else equals something else in there. And these are also indicators for languages. So some of the languages are not very informative. So if someone just numbered the languages, then we have to figure out what language 1 and what language 2 is. Now let's go to features. So now we have like candidates of paired documents. And one thing that should be clear, that if you have an English document and a French document, they should be roughly similar in size, although they might differ in a very systematic ways. Maybe French documents on average are a little bit longer than English documents. Another thing how you could maybe check if documents are aligned is by their HTML structure. So you have all these tags, and if two documents have a similar tag structure, then maybe there are translations of each other. This includes links to the same images and so on. So for instance, if two documents link to the same image, that's also a pretty strong indicator actually that there might be actually aligned documents. So this is what you could do. You could linearize the structure of a HTML document by just having these artificial tags. These are just kind of variants of the HTML tags, and then we don't really care what the content is. We're just going to say there is some content and has a certain length. And then you can figure out how to align this best based on HTML structure. And if things align pretty well, then this might be document pair, and this is also a first step towards sentence alignment. Obviously, you could also look at the content. So how similar is the content on the English document and say the French document? And you could look at very simple things. So are the same numbers and names in the documents? This is often quite effective. But for most words, you might have to translate them. And you could use a lexicon, so a collection of words in the translations. Treat documents as bags of words, and then consider how many of the words in the English documents have translations in the French document. There are more complex models, semantic representations of document content, bag of words, and neural network embeddings. So one major challenge is how to do this actually fast for a quadratic amount of possible document pairs. So if you crawl the large website and realize that there's 100,000 English documents and 100,000 French documents, you have to consider 100,000 times 100,000. So that's 10 billion possible document pairs. And how to do this efficiently is not easy. Here's a method that was proposed by Google. So Google is famous for having really initially pushed the envelope of getting data from the internet. They had the nice advantage of already having the data of the internet on their hard drives because they're a search engine. And they basically mined all this data that they had. They didn't generally publish very much, but they did publish one method on document alignment. So their idea was to just translate everything into English. Take all the foreign documents, translate them all into English, and then it becomes an English document, English matching problem. So for each non-English document, translate everything into English using the machine translation system they had up to this point, and then basically go by finding distinctive n-grams. So don't go for the high frequency single words, but look at rare, but not too rare, 5 grams, for instance, and then use them for matching. So if you, here this is now a trigram, if you have a n-gram like this, figure out which documents they occur in. So you can basically index each document, each n-gram in which document it occurs. And if this is a reasonably sized list, so you don't want to have something that occurs only in a single document. You also don't want something that occurs in 1,000,000 documents. So now we have these document lists. So for this n-gram, there's this document 1, which is a Spanish document where this n-gram occurs. Here is document 3, which is a German document where this n-gram occurs. Obviously, it occurs in the translation of these documents. So we are mainly interested in n-grams that have doculists that are relatively short, so at most maybe 50 documents in which they occur in, and also where documents occur in that have different source languages. So we're not interested in n-grams that only occur in English documents or only occur in Spanish documents. So with that, we can get potential pairs. So basically, we have here document 1 and document 3 that both occur, that both have this n-gram. So that is one potential pair. So We now have potential pairs, and we also have a forward index that maps documents to n-grams. So when we have a document pair like D1 and D2, we can then check how many n-grams they share. So we can now score the number of n-grams that occur in both documents. We also basically want to prefer n-grams that are unique. This is done by IDF weighted vectors. So we're not gonna just look at the raw counts of these n-grams, but we want to have n-grams that are rather unusual. And then you can also look at cosine similarity of these vectors. So here's some more math to go through that. So you have n-grams, so you have the list of n-grams for a document. So this is n1, n2, and so on, how often the n-grams occur in document. Be interested in inverse document frequency for a particular n-gram. So this is the number of documents it occurs in, and then the total number of documents divided by the frequency of this n-gram in documents. So this is going to score higher n-grams that occur in few documents. And then we have this vector here where we have each element index being this inverse document frequency for all the n-grams that occur in the document, otherwise 0. So it's a fairly sparse vector, and then the score is the cosine cosine distance between these two representations of documents. Next topic, let's look at sentence alignment. So this is the problem now where we have a document pair and we have to figure out which sentences are translations of each other. There has been actually a lot of work already in the early 90s. There's a famous influential algorithm from Galen Church, which really just considered the length of sentences to do document alignment. So the idea was to find one-to-one alignment, so a sentence in the English document should be matching one sentence in the French document, but also being aware of maybe there are two French sentences that correspond to one single sentences, and maybe there are also sentences that are dropped on either side. So a good sequence, a good element in the sequence, so a good mapping of English and French sentences is one that has a similar number of words. It really just went by the length of the sentences. And then they had a dynamic programming solution to find the best sequence. There are also featurized extensions of this, which not only looked at the similar number of words, but also looked at dictionaries, maybe even induced dictionaries, and also considered things like tags, like paragraph breaks. So you rather want to match up paragraph breaks, or you first align paragraphs and then you align sentences within paragraphs. So this is sensitive to noise, however. What if you have two documents where one document has one big part not translated at all? So then your alignment method might get misled here because it just kind of keeps on aligning things and misaligns stuff down here. Okay, let's step back a little bit. At the core of the problem of sentence alignment is the problem of sentence pair similarity. So both sentences must have the same meaning. That's the core problem we try to solve. So one way to address this is taking the foreign sentence, translating it to English, and then you have two English sentences. To check if two English sentences have the same meaning, you can use all kinds of similarity measures. For instance, metrics like the blue score. Also, words, another way to check it is the words in one sentence must have translations in the other. And finally, maybe we should take a fully neural approach of that by representing the meaning of a sentence with an embedding, and then also have sentence embeddings that are cross-lingual. This is the idea behind laser. So this is a sentence embedding method that uses a neural machine translation model to induce this sentence embedding. So this looks like a neural machine translation system here, where you have like an encoder that uses kind of recurrent neural networks based on LSTM cells, which then get combined. So you have then the representations for all these words. These get then combined with max pooling into a single vector. And then that single vector is used to create the translation of the sentence. This is obviously not a very good machine translation system, because the entire meaning of the sentence has to be condensed in here, and we're losing any kind of word representations and correspondences between words. But it can be trained on parallel data, and the ultimate goal of this is really not to be a good machine translation system. The goal of this is to have sentence embedding. So the sentence embedding here is a bottleneck feature that connects the encoder to the decoder. And if you train this on French English and French Spanish, or Spanish or Chinese English and so on, you also have to have a representation that is not specific to a particular target language. It has to be able to produce output in various output languages. So it's really truly a cross-lingual representation. So here's some example of what you might get out of this is you might get sentences that have roughly the same meaning, like I enjoy food a lot or I love eating. They get the same representation because they might have the same translation into a foreign language. But then it also has sentences that have the same sentence in English and the sentence in French having the same representation or very similar representation. So you have these vectors for each sentence, and then you can look at the similarity between vectors. This is what underlies a method called Vecalign that uses laser embeddings as the core measure of measuring similarity. And the nice thing about these laser embeddings is you can then also apply it to larger blocks of sentences. So you can just average sentence embeddings over 8 sentences in sequence. And so this allows you then to come up with an algorithm that starts out with first aligning larger blocks of text, and then so it starts out with finding larger blocks and then kind of progresses over. It reduces the search space to then ultimately do the more fine-grained actual final sentence alignment. So this method also has because of this course-defined algorithm, actually has a linear time complexity. Let's go to the final step in this pipeline, which is sentence pair filtering. So we found websites, we aligned documents, we aligned sentence pairs in documents. We might have made mistakes all along the way. So we have at the end a big parallel corpus, which might be very, very noisy. Maybe the website didn't even have any parallel content at all, and we still kind of went ahead and just aligned documents nevertheless. So we have to filter out bad data. So there might be many, many mismatched sentence pairs from errors in the pipeline. So there might also be non-literal translations. So if you have a news site that has news stories published in English and French and Chinese, these stories might cover the same event, but they might actually be written for different audiences and actually might not even be translations. So even if you have the same news story published by the same publisher in different languages, those stories might not be translations of each other. There might just be bad translations, either being done by people who didn't do it very careful. Another cause of bad translations is machine translation. Maybe the translations were all generated by machine translation. So much of the parallel text that can be found on the internet is actually generated by Google Translate. So detection is hard to figure out if something is machine translation or not. it looks like very clean parallel data, and maybe that's the one feature that helps you to detect it. Maybe it's a bit too clean. Kind of sentences, boundaries are preserved. Um, there's very little reordering. The translations are very literal. There was a proposal by actually people from Google to watermark machine translation to basically hide in the translation somewhere properties that it's a machine translation. So I advise you to look at that paper by Venugopal that explains how this was done. So, and then there's also a question like how clean should the corpus be? There's a precision between precision and recall. Do you want to have super precise, super clean, super nice parallel corpus that is rather small, or do you have some tolerant for maybe more noisy data in there? So there's recently much more work on this topic. Here's some methods that have been explored. One is called dual cross entropy. So this views a sentence pair as the input and the output of a translation task, and then you can score it with a neural machine translation system. So you can actually apply a neural machine translation model pretending one side is the input and then say what score does it give to this output. And you can do this in both directions. You do want to have scores that are low and similar. So low, not slow. Another one is to actually use laser embeddings here. So we already used laser embeddings for sentence alignment, but we can also just use laser embeddings for checking if a sentence pair is a good sentence pair. There's increasingly feature-based approaches that just use these kind of features and maybe additional features. There's some simple features like are there matching numbers in the sentence pairs? Are there matching named entities? Also things like email addresses or URLs or other kind of things that shouldn't be translated. Maybe we also care a lot about is it actually good language? So we can score things with a language model. So we prefer sentence pairs where the sentences are actually well-formed sentences, lexical translation probabilities, and so on. So these features could be linearly combined. So each of these features gives a score. They could be linearly combined, or you can learn weights for them, or just generally view this as a classification problem. And the way to set this up as a classification problem is to have some positive examples. So you take some sentence pairs from clean data, and then you have a negative example. So you just take one of these positive examples and corrupt it somehow. Maybe by misaligning sentences, taking one sentence of the parallel corpus and then not its corresponding translation, but any other or just neighboring ones. So misaligned sentence pairs or just changing words in them, dropping words, adding words, replacing words. So there are several open challenges. There's currently a very serious attempt here at Johns Hopkins to work on broad crawling for parallel corpora, especially for low resource languages where parallel data is much more valuable. There are major challenges. For instance, for crawling, we just use a standard tool. Maybe we should do some more work on that. I already alluded to maybe stop crawling if there's no parallel text, so you don't waste too much resources on websites that actually don't have any parallel text. Then document alignment. We did organize a shared task on document alignment in 2016. So this is still kind of an outstanding research topic where there hasn't really been all that much work on most recently. Sentence alignment, so we use the standard tools, most recently Vecalign. We haven't really done much work on detecting machine translated text, but this might pick up again. We put a lot of effort into filtering out bad sentence pairs, so especially since bad sentence pairs are fairly harmful for neural machine translation. This is now really recognized as a major research challenge. We organized shared tasks on this for 3 years running at a machine translation conference. So there's a effort currently going on where, as I said, it's called CommonCrawl, where we actually do crawl websites, find document pairs, and basically carry out this entire pipeline continuously processing terabytes of data on machines here at the university. And that's it for today. So this is kind of maybe also a call for participation. It's a fairly interesting problem. It has actually real-world impacts of being able to build high-quality machine translation systems especially for languages that are considered low resource, where there's just not much parallel corpora exist. To how to boost performance by that, one key helpful step obviously is to have more data. Okay, and that's it for today's lecture.